Hello, everyone, and welcome back to Math and Tea, the show where we talk math and drink tea. Christmas happened. Anyways, I'm your host, Professor Joseph Van Dyke. Now, I am both a scientific researcher and a politically interested citizen of the United States, and as such, there are a few things that push my rage button faster than seeing bad science, especially bad mathematics, being used to justify bad policy. Here's one example. Now, why do scientists expect us to believe that we can predict the climate for the next century when we can't even predict the weather next week? Not only do we expect you to believe that long-term climate prediction is easier than long-term weather prediction, we expect you to believe it for a very simple mathematical reason: averaging. But first, let's take a look at what the difference between weather and climate actually is. Weather is just some measurement of the local atmosphere at a given point in time. If I were to stick my head outside, which I'm not going to do because it's cold and I'm in here with the tea, but if I were to stick my head outside and take a reading of, say, the heat, the humidity, the barometric pressure, and so on, then I have taken a measurement of the local weather. Climate, on the other hand, is the long-term or average behavior of the weather. So if I were to again go outside and take a measurement of the humidity today, and tomorrow, and the next day, and every day for the rest of winter, and then calculate what the average humidity was, I have taken a measurement of climate. And this is why it can rain in the desert and still be called a desert. After all, being a desert is a property of climate, namely low yearly rainfall. Raining, however, is a property of weather. Now, if it rains a whole bunch, then we might reassess our evaluation of whether or not that counts as a desert. But one storm does not a desert unmake. Now, weather and climate might not sound that different, but mathematically they are very, very, very far apart. So let's see a very simple model that will help us understand how averaging helps us with prediction. Coin flips. Ha! Tails. Suppose I start with a very simple request. Suppose I ask you to correctly guess 4 coin flips in a row. You've got to call each of them correctly. What are the odds of you succeeding? Well, they turn out to be precisely 1 in 16, or 6.25%, depending on what you like. Now let's ask a different question. Suppose I flip the coin 100 times, but instead of wanting you to guess each and every flip, all I want to know is how many heads come up. Can you guess that? Well, okay, coins have a 50-50 chance of coming up heads, so out of 100 flips, we expect 50 heads. That's the most reasonable guess. You know what the odds are for getting exactly 50 heads out of 100 coin flips? Well, the exact answer is 100 times 50 divided by 2 to the 100. We'll come back to that. But if we calculate out what that actually is, it turns out to be just shy of 8%. That's right. It's easier to guess how many heads come up in 100 coin flips than it is to guess 4 coin flips exactly. Averaging, man. So why does this all happen? When we try to calculate the odds, there are 2 primary factors to consider: how many total different things can happen, and the number of those things that satisfy the guess we've made. Consider guessing 4 coin flips exactly. There are exactly 16 different ways of tossing those 4 coins, and when you make a guess, you're only guessing one of those possibilities at a time. Thus, the odds are always 1 divided by 16. Now, what about 100 coin flips? That's a whole lot of different things that can occur, 2 to the 100 to be exact. And, well, okay, if you don't want to do that in your head, that's a little over 1 nonillion. However, each guess of how many heads come up can cover a lot of different possibilities. There's only one way that 0 heads can appear, namely, everything has to be tails. But there's 100 different ways that 1 head can appear. It can appear in each of the 100 different positions. And it turns out there's 4,950 ways that 2 heads can appear, and so on. The most possibilities in a single value lies at 50, which contains over 100 octillion ways those heads can appear. But you might say that's asking too much. We rarely ever want exact data. We want a range of possibilities. So in this case, that might look like allowing multiple guesses. So consider the following. How many guesses would you need to have one of them be the correct answer at least half the time? Well, if you're guessing each coin flip exactly, since each possibility is equally likely, you would need to guess half of the possible answers. In our case of 4 coin flips, that would mean you'd need to guess 8 out of the 16 total possibilities. Now what about guessing the total number of heads? As it turns out, that's a lot easier. If you guess that out of 100 coin flips, you'll see between 47 and 53 heads, you'll be right about 51.6% of the time. And 47 to 53 is only 7 out of the 101 different possible answers. In fact, if you want to guess correctly 95% of the time, then you only need to guess between 40 and 60. That's 21 out of the 101 different possible answers. Now what happens as we add more and more coins? Well, if you're trying to guess each coin flip exactly, each coin we add doubles the difficulty of doing so. Guessing 4 coin flips exactly, 1 in 16. 5 coin flips, 1 in 32. 6, 1 in 64. And if we're allowing multiple guesses, you still need roughly the same amount no matter how many coins you have. You'll always need to guess half the possibilities to be right half the time. However, when we're looking at counting how many heads appear, in order to double the difficulty, you need to roughly quadruple the number of coins. Guessing 50 heads out of 100 flips, roughly 8% chance. 200 heads out of 400 flips, roughly 4% chance. 800 heads out of 1,600 coin flips, roughly a 2% chance. To guess how many heads came up in 100 coin flips and wanting to be right 50% of the time, we needed 7 total guesses, roughly 7% of the total number of possible answers. With 400 coin flips, you need 14 answers. 193 through 206 will do the trick, which is around 3.5% of the total possible answers. Again, quadrupling the number of coin flips roughly doubles the length of the interval you need to consider. But that's quadrupling versus doubling. So in some sense, it gets easier to guess the average answer as you flip more and more coins. Now, I really want to emphasize something here. I've been using coin flips as my example so far because, well, they're something everyone understands. They're a very simple model of a random thing. But the reason why weather is hard to predict is not because it's random. It's because it's chaotic. Here's what I mean by that. When we're trying to predict the weather, what we're doing is we're taking a bunch of measurements right now and feeding them into a gigantic mathematical equation. Now, if we had exact data and infinite computing capacity, we could theoretically predict the weather with perfect accuracy as far out as you want. But we don't. We have imperfect data and only a little bit of computing capacity. In other words, we have errors. And each time we run those calculations to try and predict the weather a little bit further off, those errors grow. That's why the accuracy of the weather forecast tends to drop off day by day. It starts off pretty well today and tomorrow, but as we keep going on and on and on, well, it starts becoming not so helpful. But even in chaotic, not necessarily random systems, we still have averaging as an incredibly powerful tool. When we're trying to predict the weather, we don't have any idea whether or not we've overestimated or underestimated something. We don't know which way the error is pulling us. But when we average out over a long period of time, we can guess that we probably overestimated as often as we underestimated. And that is how averaging can turn an impossible problem into a completely tractable one. But that's all for now because, yeah, I'm out of tea again. Bye.